Things fall down thanks to the gravity. It's one of the defining features of life and physics on Earth. So, how to explain the chain fountain above, in which a 50-meter string of metal balls briefly flows up before plunging to the ground? Steve Mould, the BBC science presenter, whose YouTube video published in 2013 drew a lot of attention to the weird phenomenon, has one explanation. The chain, which has to travel over the lip of the beaker before it can make its downward turn, is moving so quickly that it can't instantly change direction. Instead, it continues to traveling up for a bit, changing direction slowly over the course of a loop. But when two Cambridge physicists, John Biggins and Mark Warmer, tried to write an equation describing the chain fountain's behavior, they discovered that Mould's intuitive explanation was wrong. They theorized that the creation of the flowing loop depends not on inertia, momentum, or gravity, but rather on the upward force coming from the bunched up end of the chain still in the beaker. Still, the physicist model doesn't explain what causes the twists and waves at the top of the chain, leaving room for more theories. So now, let's take a closer look at how this great phenomenon happens.
Objectives. Our main goal is to analyze the chain fountain phenomenon, going deeper with the discussion into why it happens, and have a detailed view of its dynamics. The phenomenon required a certain structure of a string, just like beats. Therefore, our group wanted to see if this effect would happen with different materials and different heights, in order to explain the nature of the phenomenon. Methodology. We studied two main parameters relevant to the phenomenon, the type of chain and the type of container. On Table 1, we listed 3 different chains we tested and their properties. For consistency, the same person was responsible for each chain throwing process. We performed 5 tests for each specific condition for the sake of statistics. Each test was filmed with a proper scale, reference, and the footage was analyzed by a tracking software to see the maximum height the art got through. Discussion. To see what was really altering the effect, we thought of testing with different variables. So we proceeded to throw 3 different chains from the same container. A metal beads chain made out of stainless steel. The second one was made out of plastic and string. The third chain was a regular metal chain, also made out of stainless steel but with a different structure. Our first idea was to film the effect with the chain inside of different containers to understand what could happen after it and how the effect behaved. Since we have chosen to test only the metal beads chain, we decided to test it with 3 different types of containers. A small plastic one, a 400 milliliters beaker, and a plastic wrap on top of a stainless steel can. Then, we made graphs on how the chain would behave in each one of these containers.
Conclusions. As we can see from the graphs, the height of the tip of the arc has a tendency to increase over the course of time. This brought us to the discussion that if it is increasing over time, the resulting forces the chain is leaving the container might point upwards, so the known forces acting on the chain are gravity and traction. Furthermore, these experiments led us to believe that the force which makes the chain rise comes from inside the pot, as the effect was more apparent when we tested with the glass beaker, which, because of its rigid bottom, made the chain rise higher, and this theory checks the Cambridge physicists' one. In order to have a better understanding of the kickback force the bottom of the pot causes to the chain, we tried to simulate the phenomenon on the floor to analyze how the end of the chain that is not being pulled behaves. As we drew a line where the chain was initially positioned, we could clearly see that the chain gently receives a push downwards, which would be the part of the chain in contact with the bottom of the pot. This corroborates the reaction force provided by the pot as the chain flows down out of it. Moreover, we noticed that by the end of the experiment, as the chain gets to the floor, it receives a sort of boost that makes it go higher, experiencing a sucking effect. To test this phenomenon, we let go of an object and a piece of the metal beads chain at the same time and height, and we noticed the chain indeed reached the floor before the object. In addition, we decided to mark the chain when it reaches the floor, 6 meters and 71 centimeters. With a pink sticker to analyze if it would go higher as we see the sticker leaving the pot, which means the other end of the chain would have reached the floor. After 3 tries, we could conclude it certainly went higher as it got to the floor.